Medhavy AI, Intelligent Learning Systems. In this deep dive, we unpack the free particle and wave packets, Chapter 8 of Quantum Mechanics, Volume 1. Let's get into it.
Start with the simplest physical environment imaginable, a single particle existing in a complete, infinite vacuum, where the potential energy is exactly zero. To find out how a quantum system behaves here, we write down the time-independent Schrödinger equation, dropping the potential energy term entirely. The mathematical solution to this simplified equation is straightforward. It yields a pure plane wave function. Psi of x equals a constant, a, times the complex exponential e to the ikx. This specific solution carries a perfectly definite, exact momentum. We calculate that momentum by multiplying Planck's reduced constant, hbar, by the wave number k. Physically, this complex exponential describes a uniform oscillation. It repeats endlessly, spanning across all of infinite space, without ever changing its amplitude. To translate that abstract wave function into a measurable probability of finding the particle, we must take the absolute square of the wave function to find the probability density. Solving the simplest possible equation in quantum mechanics leaves us with a mathematically perfect wave, but one that stretches endlessly in all directions. This diagram illustrates the probability density for that plane wave. On the left, the oscillating wave sits beneath a perfectly flat horizontal line. This constant probability density is distributed evenly everywhere. Integrating this constant across infinite space yields infinity, breaking down the mathematics. This mathematical failure carries a specific physical meaning. A particle with exact momentum becomes completely delocalized, existing simultaneously everywhere and nowhere in particular. A real-world physical particle cannot exist like this. It must be localized within a bounded region of space, where a detector could actually measure it. A pure energy eigenstate cannot possibly represent a physical free particle. The simple plane wave model fails the test of reality, forcing us to abandon it entirely. The formal solution to this normalizability crisis relies on a mathematical tool called Fourier superposition. We have to build a new state out of multiple waves. Instead of using a single plane wave with one exact momenta, we integrate over a continuous range of slightly varying momenta. Mixing these different frequencies aligns the waves to constructively interfere, creating a localized bell-shaped peak. Outside this peak, they destructively interfere, leaving flat tails of zero probability. Because this bounded packet is finite, its probability integral yields exactly 1, mathematically resolving the crisis. Creating a localizable physical particle strictly requires a mathematical mixture of multiple overlapping momentum states. With a localized wave packet built, we have to analyze its dynamics, specifically how this constructed object physically moves through empty space over time. The relationship between the wave's frequency and its wavelength is governed by the free particle dispersion relation. Angular frequency, omega, equals hbar times k squared divided by 2m. From this, we define the phase velocity. This is the speed at which the individual internal wave crests travel, calculated simply by dividing omega by k. When we substitute our dispersion relation into that formula, the phase velocity reduces to momentum divided by 2 times the mass. This exposes a glaring paradox. Classical mechanics expects a moving particle's velocity to be momentum divided by mass. The wave calculation yields exactly half of that expected speed. The true particle is the orange bounding envelope, traveling at the group velocity, the derivative of omega with respect to k. This calculation yields momentum divided by mass, recovering exact classical velocity. Watch the faster orange envelope continuously outpace the internal purple crests. Phase velocity is merely a mathematical artifact of the wave's internal structure. The group velocity governs the true, physically measurable speed of the quantum system. Building a localized packet out of multiple momenta triggers an unavoidable mechanical side effect, dispersion. Within the Fourier superposition, the constituent waves hold different momenta. The components carrying higher momentum naturally travel faster through space than those carrying lower momentum. Because of this speed differential, the faster-moving components at the front of the packet outpace the slower-moving ones trailing at the back. This creates a strict contrast between position space and momentum space. On the left, the position density peak moves forward while visibly widening and flattening. On the right, the momentum density peak remains perfectly static over time. While the spatial probability constantly spreads outward, the underlying statistical mix of momenta required to build the packet never changes in empty space. This establishes a counterintuitive mathematical trade-off. Forcing a tighter initial spatial squeeze on the packet requires mixing in a much wider spread of internal momenta to construct it. Constraining a quantum particle to a highly precise location guarantees a violent internal divergence of its component speeds. The rate at which this spatial dispersion occurs is governed by an exact mathematical scaling law. This graph plots the position spread of an electron over time. It tracks three distinct initial widths, 0.5, 1.0, and 2.0 nanometers, tracing three separate parabolic curves. The exact time it takes for a wave packet to double in width scales directly with the square of its initial width. A tightly localized electron violently disperses almost immediately, climbing sharply up the y-axis, while a wider packet maintains its original shape far longer. This spreading behavior is the direct mechanical consequence of the Heisenberg uncertainty principle. A sharp position requires broad momentum, and broad momentum forces rapid dispersion. This completes the physical picture of the quantum-free particle, built piece by piece from a mathematical abstraction into a functional, localized structure. A true physical free particle is never stationary. It is a strictly dynamic superposition that travels and inevitably disperses across space.
That was a Medhavy deep dive. Medhavy AI-powered intelligent learning systems on YouTube at Medhavy AI, medhavy.com. Subscribe for the next chapter.